So in my last video, I finished and said that the series on parabola was too long for a single video, and this is a part 2 of the series, and there will be a part 3 after that. So now I want to prove that when we have a curve of equation y equals x squared, then all parallel rays that will come towards the curve, light rays, will be reflected to the same point. So if we recall, in optics, if we have a surface, any ray that comes to a reflecting surface will be reflected with the same angles here, θ1, θ2, or sometimes you can see them with respect to the normal to the curve. And of course, now here we don't have a straight surface, we don't have a plane here, we have our line, we have a curved surface, and what we do obviously is we will calculate the tangent to this curve at any point to see where the reflection will go. And how will we do that? Of course, when we have the equation for a curve, the tangent is the slope of the tangent is given by the derivative. So this thing has a slope of 2x, and we use the well-known fact from geometry that if you have a straight line and another line perpendicular to the first line, the product of their slopes is equal to -1. So this thing has slope equals to -1 over 2x. And what we want to know is basically we know everything about this thing. We know that it's a vertical ray that's coming parallel to the y-axis, and we know it's coming at some coordinate x. So to avoid any confusion between the general equation of the curve and this point, I will call this point x0, y0. And we know everything about this thing because we know the slope here, we know the slope here, and if we really want to, we can calculate the equation of this line. Of course, I will not do that because that's a lot of calculation that it's not really useful, because what we want to know basically is what is the direction of this ray. And what I do to calculate that, I will use the fact that the dot product between two vectors gives us the cosine of the angle between the vectors multiplied by the norm of the two vectors. So if we remember, if we have a vector A dot product of vector B, this is equal to the norm of A times the norm of B times the cosine of the angle between the two. And here, of course, if the angles between the incident ray, incoming ray, and the reflected ray are equal, the cosine of the angles will be equal. So if I name this vector here, I will just remove that because I will just take it in this direction. Doesn't matter one or the other. This will be the same thing, but I will just name this one A. And this thing here, I will name it B. And the vector along this line here, I will name it C. And if the cosine of the angles is equal, this means that A dot B over the norm of A times the norm of B is equal to, A dot B, this is not the right thing, A dot C is equal to B dot C over the norm of B times the norm of C. So it's basically saying that the cosine of the two angles are equals. Now we see that, the norm of C, obviously. The norms of C are present on both sides of the equation, so they cancel out. And what we'll do is with C, we know what A is, we know what C is, and we're looking for B. So our setup will become A. I will just simplify calculations by taking it of norm 1, and take it at 0, comma 1. So this is a vector that is parallel to the y-axis. C is a vector along the line. Well, I will take 1 minus 1 over 2x0 because we calculated the slope is minus 1 over 2x for all x. So minus 1 over 2x0 over 1 gives us something that has a slope minus 1 over 2x0. And b, well, we don't know what b is, so just we take it 1 and some variable v that we have to find. And so what we do now, we just calculate all these quantities, the dot product, the norm of A, the norm of B, equal them and do some algebra to get an expression that will give us V, basically, which would give us the direction of this vector here as a function of the position on this curve y equals x squared. And then we can, using this gives us the slope of a line that is along the direction of B. We will be able to see what is the intercept with the y-axis. So just doing our calculations, a dot c, that's pretty 0 times 1, that's pretty easy, minus 1 over 2x squared, so that's my 2x0, sorry, minus 1 over 2x0. And that's equal to, because the norm of a is equal to 1, basically, b dot c, so that's 1 minus v over 2x0. And we have to divide by the norm of this vector b, which is the square root of 1 plus v squared. We can rearrange these terms, raise this one on this side, write this one on this side, and we will get the square root of 1 plus v squared equals to, well, we can keep the minus sign here, 2x0 minus v. And now we can square both sides, because if these two things are equal, then their squares are definitively equal. And we will get 1 plus v squared is equal to 4x0 squared plus v squared minus 4vx0. And then we can go back here and see that the v's will cancel out. And now we have something that's linear in v, so we can isolate v pretty easily. Put this side on the others, with this term on this side, 1 minus 4x0 squared. There's a minus, we will just get rid of it by reversing these terms. And that means that 4x0 squared minus 1 over 4x0 is equal to v. So now we have a vector, and on the next board, I will calculate the equation of this line here, and we will see that the intercept with the y-axis is independent of the point we selected initially. So I will just keep this here and continue the calculation on the next board. Okay, so we know what the slope of this line is, because basically this line is parallel to the vector b, which was of coordinates 1, v. So we know that this line here has equation y equals mx plus k. It is a line that is along the reflection of this ray coming from infinity. And we add that v is equal to this thing, so the slope is simply equal to this thing, v divided by 1, and we add y equals to 4x0 squared minus 1 over 4x0 minus x plus some offset k. Now, how do we get this? Well, we know that not only this line will intersect the y-axis, it also intercepts the parabola at coordinates x0 y0, and y0 is equal to x0 squared. So we can just plug back x0 squared equals to 4 x0 squared minus 1 over 4x0 all multiplied by x0 plus k. Now this x0 can be divided on both sides, or even better, we can just multiply these two and get rid of it. We can get the 4 up and distribute it to the k, and we will get 4x0 squared equals to 4x0 squared. We like it because that means things will cancel out. Minus 1. Don't forget that this x0 has been cancelled by this one. And we don't forget the 4 here that has been multiplied on both sides, plus 4k. And we will be very happy because now we have 4x0 squared, for example, that cancels out. And we have k equals 1/4. What does that mean? It means that whatever point we are here on the parabola, the intercept of the y-axis of the reflected ray will be at y equals 1/4, because we have an equation of the form y equals mx plus k. If this is 0, y equals k, so here 1/4. So we proved that all the light rays would intercept the y-axis at the same y-coordinate, which means that all the rays would be reflected to this point, which we'd call the focus. And I won't do the reverse in details, because basically what you do is you suppose that you have this setup, you have these things that all reflect to the same point, and you take all these steps, but you do them in reverse. And if you do them in reverse, you will see that if this is true, if all the rays are reflected here, then we must get the slope of this thing equals to minus 1 over 2x, which means that the tangent to the curve is equal to 2x, which means that the curve here has equation dy dx is equal to 2x. And of course, the solution to this differential equation is y equals to x squared plus a constant, which is a parabola. We just wanted to prove this was a parabola. We don't even need to prove that this is the constant is equal to 0. We proved that if we start from this, we get to the first definition. It is a parabola. And now what I will do is I will look at the relationship between these two definitions without necessarily using the algebraic equation. So this is the end of part 2, and I will get part 3 up pretty soon.